Perfect. Okay, welcome to trigonometry. Whew. I'm glad I had you guys all for Algebra 2. This is so cool. We're going to continue on. So this is hopefully will be super cool and awesome. So let's talk about the syllabus first, just so we orient ourselves. And please ask any questions if you have them as we go through it. So trigonometry, both first, second semester. Here we go. So trigonometry is really just a lot of algebra, a lot of geometry fused into thinking about a triangle. Oh man, in fact, like trigonometry and metry is measurement, right? At the end, and tri, just it's a triangle. So it's measurement of a triangle. Could you imagine? Whole years just in terms of looking at a triangle. Crazy stuff. I had, when I was in college, we took a whole semester to take a look at, oh, you know, I equals the square root of -1. We took a whole semester just to explore that. And then there's 2 more other classes if you want to explore it even more.
What the heck?
So
This is why I'm not doing that.
Whole new world called complex number system. Oh, and the funny thing is, when they have something called elementary complex numbers, then they have intermediate complex number, and then advanced complex numbers. So yeah, craziness. Yeah, see, there's 6 of you guys. Yeah, so get away from everybody if you want. Absolutely. Yeah, seems like it's closer this way if you are. That's cool. Okay, honors expectations, here it is. I know some of you guys are in honors, some of you not. Here's the difference in my mind. Here's what I think is, first of all, you will have extra homework assignments. I can roughly 3, 4, 5, 6, 7 more questions or so on the homework. Those will correspond to a, when you guys take the exam, there will be also an honors section for the exam. And these questions are going to be a little bit more abstract, kind of getting your sort of way more of understanding towards, gearing yourself towards calculus and physics, because that's what tends to, you're trying to be driving for. Okay, and then also on the oral final, as you guys all from last year, you'll have a little more questions to choose from. So it'll be a little bit more of almost like a complete list. If you know those questions, if you've memorized them, you definitely know this class first semester. So take that into account. There's the difference between canon and honors. All right, the textbook that we're using, you guys should all have it already here, is like this guy. And it's written by McKee. McKee is a professor actually down the street here at Cuesta College. And he's pretty well known for writing books. He wrote books for quite a while. And then about 4 years ago-ish, he decided textbooks are too expensive and I'm gonna make my own company, and no textbook is gonna be over $100. And so he did it. In fact, we use his algebra stuff, his own publishing company at the college level. And sure enough, yeah, they're like $45 or something like that for a math book, as opposed to 100. I think we even had in college, just for the fun of it, we try to figure out what's the most expensive college textbook ever. And it came down to between like a microbiology book and a business book, and they were roughly $400, $420 or something like that. So most expensive college book gets the prize. Okay, we good there? There it is. Methods, we're going to meet Monday, Wednesday, Fridays. We're going to do lecture. We're going to do some extra assignments. I'm going to give you guys stuff to do, all the good stuff. Also, let's see, also challenge. That's right, challenge problems is another thing for honors. I'm going to give you guys challenge problems. Honor students, they have to complete a certain number of them. For canon students, they don't have to complete any. It would just be like extra credit. So there are kind of distinctions there. Okay. If they want to reveal themselves, they can. Wow. Okay, grading system. Yeah, grading system exactly as it was last time. So final, split into 2, a written and an oral. 20% for exams and quizzes. 20% for that project presentation and challenge questions. That's what they fall under. And then the homework assignments and the class participation, that's kind of me gauging how well you interacted in class. Okay, we're good. Any questions on the syllabus? Because I'm done with the syllabus. Okay, late work. Late work, if you trim, there's gonna be some kind of penalty for that. And then with parent roles, if you choose to, it would be great for you guys to discuss what you're learning in class, if they don't ask already. Abe.
Are we turning homework in by hand?
Yes, absolutely. Homework goes in by hand per section once we finish with that section. And roughly the way I think about it is like if we lecture on one section now, then you have till like Wednesday to do it. And then it's due that Friday or something, you know. So you have one day to sort of correct your homework if you need be, and then it's due the next section. So two class sessions away from the time we finish. All right, so for grades, I am still going to use the Google Classroom system, just in case we have to go online or something like that. At least we can go that way. Still turn in paper pencil homework on here. The due dates on the Google Classroom may not reflect the true due date. We're good. I'm going to put it on there. But in case we're running late on something, or in case we took the extra time to do something else. So true due dates are going to be what we talked about in class. And do you guys all have a planner or no? You guys usually put stuff in a planner? Raise your hand if you have a planner and you use it. Oh, Dylan just memorized everything. Okay. Okay. All right. For Google Classroom, I do need your email, so then I'll send out an invite for that, and then I'll hopefully get all that set up this week. Okay, good there. Any questions on Google Classroom? We've used it. I think we're pretty all used to it. All right. Class expectations here is that you have attempted the previous homework, and then at least scanned the next section. Please do that. I think it's going to be super helpful for you if you're going to be doing. We're doing finished up 2.2. We're going to do 2.3. At least thumb through 2.3. Just sort of like, hey, that's what we're going to talk about. Oh, that's the extension. Oh, that's why it's different from 2.2. All right, and then also watch the time for me. We go from 9:55 to exactly 11 on Monday, Wednesdays. I will try to check the time, but sometimes I get so super caught up in trigonometry, I forget what time it is. And so if we're getting close to 11, just remind me. On Fridays, if it goes to 10:15, remind me. Tristan.
They added more in that.
It's also because we the 0 period is a bit longer, so people will class.
And then we started first period a little later for the walk up here, and then to get people situated there at the bottom level. And then real quick here, how many just out of curiosity, who does not have class after this? You get like a free class. Is everybody in another class after this? Oh, gotcha. Okay. In the same classroom even?
Yeah.
Okay. Yeah. All right. Okay, so trig book, here it is. We're going to cover all chapters here, 1 through 8. Philosophy of homework, which you probably already know, is we take notes, and then the problems, some of them should be exactly like your homework, and then your homework is going to be a tiny bit more complicated. The answers are in back of the textbook. So go ask, which my little thingamajiggy is go ask Bob. Back of the book. Mr. Bob. Okay, so let me hand out the homework sheet to you guys, very similar to what we did last year for all right, so let's see, not like last year, there's no vocabulary piece to it this time. It's just problems themselves. The ones in front are for advanced students and honors. The stuff in brackets are additional ones for honors. And let's talk about 1.1. So for chapter 1 class, I just said start already preparing for it here. I'll give you guys a study guide. All right, 1.1, what are we going to do? We are going to review angles, we're going to review triangles, all the stuff we should remember from geometry. Pythagorean theorem, and then we got two special triangles that we need to think about, and transitioning to the special triangle rule trigonometry. So two special triangles that come out of geometry, which is the basis for trig. 1.2, we're going to review the Cartesian coordinate system. Remember distance formula, remember graphing circles, all the good stuff here, and drawing angles. And then weird stuff. You guys ready for this? Trigonometry has 3 different definitions. There's definition 1. 1.3 is now is definition 1. We'll eventually get to definition 2 and definition 3. We use them based upon the situation. That's what we learn. So we'll hopefully learn when those are. Okay, 1.4. Once we learn definition 1, 1.4 is all the different identities that come out of it. There are 3 different types. There's called the reciprocal identity, or the ratio identity, and the Pythagorean theorem identity. And then after we build those guys, we're gonna 1.5 is gonna be a whole bunch more identities. So there's like this interconnected puzzle of trigonometry. There's a whole bunch of different things here that all kind of just smush together because they're so interrelated. And so there's a homework for that. Dun, dun, dun. Okay, we jam. Let's keep on jamming. You guys talk to me about taking notes here. How many are familiar with the Cornell note-taking system? And how many like the Cornell note-taking system?
I know it.
Know it and hate it. Know it and hate it?
I take my own notes.
Okay, your own notes, the way you've developed them, the way you are, okay?
The Cornell thing, like, it's basically just like normal notes, and you come back and write a summary. But I never ended up writing a summary, so I rather just like take bullet point notes than use them.
Gotcha, okay. Okay, then we'll skip that. Awesome. Natalia, what kind of notes system do you sort of do?
I pretty much just use bullet points and then look over them.
Okay.
Like you said.
Okay, similar. Okay, gotcha. And Dylan?
Honestly, it's a combination of bullet points, occasional sketching, and
Okay, okay, gotcha. Okay, come back around here, Tristan.
I just kind of write stuff.
Just write stuff down. We go with it, and then it makes all sense. Cool, Dylan.
Real associative, note taking, like, because I know if I write something down, I'll probably remember something else. I can always do that.
Okay.
It's like kind of like not shorthand, but it's an easy way of taking that. But if I go back and I read it, it'll make my brain remember other things.
So as you write down stuff, you try to associate with stuff you may have known earlier, or kind of like jot down stuff that you mnemonically remember. Okay, cool. Isabel, how about you?
I don't know, I like making lists and I write as much as I possibly can down.
Okay, gotcha. Sounds good. I just want to make sure that you guys have developed your own notes taken. Oh, how fun. So puzzle things, we can try it out. If you could do it quietly at your desk, that's fine. If you can still follow along. I was thinking that is more like lunchtime or break or something like that, where like you're just bored. Okay. So just real quickly here, I'll change this up every like 3 or 4 weeks. So we have the 2 puzzles here. Okay, just trying one. You just need to figure out how to separate these guys from each other. Very easy, no problem. Anyways, try to separate those, and we'll put some fun stuff there. And then, since we started the school year, if you want to see yourself in the years prior, I have the 2 prior years.
Oh, that's just me.
Okay, and then this one right here is, I photocopied all these from here. So if you want to learn a little bit more about William Isaac Newton or Banneker or Lagrange. And so if you want to take a look at it, you can take a look at it. And then all these kind of different, they're kind of geared more toward like middle school. But just kind of some fun stuff each of these came up with. So that's headed under each person, like Nikkei right here. Nikkei talks about him a little bit here, and then it talks about what he did. What did he do? You get a cool thing. I'll show you one story. So Nikkei comes from a pretty rich family here. He owns land, and he figures out some reason, some person has been taking stuff from the storage. From what I understand, they have a basement area, right? And they had goods in there. So one or two or more of the workers were actually stealing things from the base, you know, because it's for workers. So he said, I'm gonna figure out how this supposed to happen. So he said, okay, he lined up all these people. And he says, someone's been stealing the goods from downstairs, from the basement area. So this chicken that I have, or there's a chicken downstairs. But what I want you guys to do is, I want you to walk downstairs and you're gonna pet the chicken. And the chicken's gonna know whether you are telling the truth or not. So, you know, the workers, one go down. And then, you all stand up straight and they have everybody like show their hand. And he knew exactly who was the thief. Because he put a little charcoal on the feathers of the bird. So people didn't have a guilty conscience, they just went like this and they came back up, right? The person that had a guilty conscience, he walked down there, I'm not gonna touch that chicken. So he walks up and he raises his hand, his hand is still clean. And so he's the guilty guy. So kind of fun.
That is already be caught. I think a chicken can smell the lion.
Remember, from Algebra 2, remember Nikkei's rods? That's the same guy. No one remembers Nikkei's rods. Here's your rod system. It's the way that you can multiply two numbers together real quick by using, or Nikkei's bone, sometimes called. Oh, and this is cool. Look at this. Did you guys know there are 5 different ways to multiply? 5 different ways to multiply. There's the Thai method, there's the that we use, then there's something called the Russian peasant method. Just a different way to multiply. Anyways, just if you're curious into any one of these people up here, just for the fun of it, and I'll try to change it up every so often. Okay, and then the fun part, I guess a quick video. I'll try to do maybe like fun videos of the day or something like that, which I find it interesting for me. And then we'll go for it and then we'll start class here. So this one, usually they're maybe like TED Talks or something else like that. And then the volume doesn't like me here.
How many of you are creatives, designers, engineers, entrepreneurs, artists, or maybe you just have a really big imagination? Show of hands. Okay, that's most of you. I have some news for us creatives. Over the course of the next 20 years, more will change around the way we do our work than has happened in the last 2000. In fact, I think we're at the dawn of a new age in human history. Now, there have been 4 major historical eras defined by the way we work. The hunter-gatherer age lasted several million years. And then the agricultural age lasted several thousand years. The industrial age lasted a couple of centuries. And now the information age has lasted just a few decades. And now today, we're on the cusp of our next great era as a species. Welcome to the Augmented Age. In this new era, your natural human capabilities are going to be augmented by computational systems that help you think, robotic systems that help you make, and digital nervous system that connects you to the world far beyond your natural senses. Let's start with cognitive augmentation. How many of you are augmented cyborgs? I would actually argue that we're already augmented. Imagine you're at a party and somebody asks you a question that you don't know the answer to. If you have one of these, in a few seconds, you can know the answer. But this is just a primitive beginning. Even Siri is just a passive tool. In fact, for the last 3.5 million years, the tools that we've had have been completely passive. They do exactly what we tell them and nothing more. Our very first tool only cut where we struck it. The chisel only carves where the artist points it. And even our most advanced tools do nothing without our explicit direction. In fact, to date, this is something that frustrates me, we've always been limited by this need to manually push our wills into our tools, like manually, literally using our hands, even with computers. But I'm more like Scotty in Star Trek. I want to have a conversation with the computer, right? I want to say, computer, let's design a car. And the computer shows me a car. And I say, no, more fast looking and less German. And bang, the computer shows me an option. Now that conversation might be a little ways off. It's actually probably less than many of us think. But right now, we're working on it. Tools are making this leap from being passive to being generative. Generative design tools use a computer and algorithms to synthesize geometry, to come up with new designs all by themselves. All it needs are your goals and your constraints. I'll give you an example. In the case of this aerial drone chassis, all you would need to do is tell it something like it has 4 propellers, you want it to be as lightweight as possible, and you need it to be aerodynamically efficient. And then what the computer does is it explores the entire solution space. Every single possibility that solves and meets your criteria, millions of them. It takes big computers to do this. But it comes back to us with designs that we, by ourselves, never could have imagined. And the computer is coming up with this stuff all by itself. No one ever drew anything, and it started completely from scratch. And by the way, it's no accident that the drone body looks just like the pelvis of a flying squirrel. It's because the algorithms are designed to work the same way that evolution does. And what's exciting is we're starting to see this technology out in the real world. We've been working with Airbus for a couple of years on this concept plane for the future. Now, it's a ways out still, but just recently, we used a generative design AI to come up with this. This is a 3D printed cabin partition that's been designed by a computer. It's stronger than the original, yet half the weight. And it'll be flying in the Airbus A320 later this year.
That's cool. You good there? Video of the day. I thought something that I find interesting, but this whole concept of computers, not AI specifically, but being able to amass really quick here all the different possibilities, calculate them, because that's what we make computers for, right? Calculating machines. But if they can do it in geometry space with certain preconditions, wow, that's interesting.
That's something that will be more possible once like quantum computers are.
Sure, yeah. And he said it takes big computers. So I'm sure it's a humongous integration of multiple computers to get that happening.
Because the computers that we have right now are not as fast as they can be, but like there's going to be a point soon where we can't make computers where we do in the past.
Mhm.
So we have to start with quantum computers.
Sure, absolutely. Talk about.
Because it's very hard, so we don't understand the whole. We actually do.
Well, we don't have the capabilities to make computers.
Oh, we also know that the thing is that we can't, it's very hard to maintain the environment that the particles need to be very rapid against. So they have like really sized fridges with a lot of ones. So, figure that out. We won't.
Okay, I'm gonna ditch the Cornell note taking because you guys don't like it. So let me jump to and make myself just a blank space. Okay, that should be enough for us to get going on. Good. Okay, are we good now? Let's jam with. Let's see, I think I got it in the smallest version possible. Yep. Okay, so let's go with notes here. What time is it? 11. Got 40 minutes. Okay. So chapter 1, what's it all about? We have the 6. Write that in so it's a little bit better looking here. The 6. trig functions here. So that's chapter 1. What we're going to do first is just angles, go back to geometry. We're going to touch upon angles, degrees, and the special triangles. That's going to set us off into trigonometry right there. So we have angles in general. All right, lots of writing stuff. We're good. Angles. How we think about angles is like this usually. Hopefully remember this from geometry. It looks like that. And then what we do in trigonometry particularly is we say which direction it's going to go. So we kind of go like this. We give it a direction. Then we have different symbols for angles. So the most common one is something called theta. It's kind of like a 0 with like an extra piece slid on it here. Sometimes we use alpha, which is the Greek letter. Sometimes we use beta. And beta, it's not like a V. It has this little extra little piece on the bottom and an extra little swing in front. Okay, and then also sometimes we just use the capital letters. So ABC usually. And I think you've done in geometry ABCD triangles, right? And stuff like that, where you did the vertices. Just real quick here, just so we have it here. So alpha. Let me do the first one here. Let me do theta first. So this little guy right here is called theta, Theta. That's alpha. And this one, like an extra little curve there. That's called beta. Are we good? Easy enough there. Okay, which way do they spin? So now spin of angles here. And so we have this one like this. Oh, you know what we should do? Just real quick here on the previous slide. We also have, which I'll talk about, this is called the initial side. And this little piece right here is called the terminal side. So where does this start? Where does it end? Important parts. And so if the initial side is a certain place, we call this a angle in standard position. If the initial side is somewhere else, then forget it. We don't call this standard position anymore. Okay, we jam? Are we good there? Tell me if I'm going too fast and we'll kind of gear our way through it, okay? You get to put it wherever you like. And we'll talk about if you put the initial side in a certain spot at the vertices of the x-axis, and you put the initial side on the positive x-axis, that's called standard position. But we'll get there once we get to 1.3. So just the fact that you have an initial side of an angle and you have the terminal side where it ends. Okay, are we jamming? Are we good? Okay, the spin, here it is. So we have, so here. All right. So if it goes this way, we consider this a positive angle. Did you guys ever do negative angles in geometry or no? No, I don't think so either. Huh? I've never seen it. I'm thinking of geometry days here. So what makes a positive angle is that it turns counterclockwise. So against the clock. That's what's happening here. Positive angles are against the clock. Then we can actually go the other way. We can actually have a negative angle, it just spins this way. Spins down now. negative angle, and we turns. Clockwise. Are we good? Jam, and that's the other two. Now let's talk about degrees. It spins clockwise from the initial side. Once it starts spinning clockwise. Tristan, did you do it? Did you separate them?
Abe did. I'm trying to figure out how to put it back. I don't know how to put it back either. Yeah, I already did it.
Cool. Okay, let's keep on going. Just make sure that that does not disturb you from actually taking notes themselves, though. Okay. Okay, so degree measures. Let's do that here. So first things first, let's just remember here, look, this is crazy. Initial side becomes final side. And it goes like this. There's my theta. One rotation. How about one rotation is 360 degrees? So I took the initial side first, laid it out, and then I circled all the way back around, back to the initial side. That's what that arrow is reminding me that I did. Perfect. Yep, positive rotation. Now, could I go a negative rotation 360 degrees? Absolutely. And it'll be negative 360 degrees.
So when we're drawing angles from now on, maybe the little arrow thing.
Yeah, Okay, let's see. And this concept of, notice it's not, it's 360 degrees. It's actually a base of 60. It's actually 60 times 6. Where does it come from? Man, it comes all the way from the Babylonians. Babylonians had a base 60 system. What's our base system? 10, right? Because we have 10 different characters, right? And then once we run out of those characters, then we start combining those two characters together, right? Once we stop all the different combinations of the two characters, we build upon a 3-character system, right? And so Babylonians did the exact same thing. And so their system was like that. And Babylon, it's crazy because you read in history, these guys were not just an empire. They were like the empire of the ancient world. They controlled so much. They made a universal language, which is cuneiform, and a written language. So they, huge society. But they had a base 60 system. They thought the number should extend out 60 pieces. And we still use it, right? Give me some base 60 systems we use here. What do you guys say?
Minutes?
Minutes, and seconds, right?
Oh, yeah, an hour. Not hour.
That's right. Yeah, hour actually is kind of funny, right? Hour is a 24 base system, right? And then we go back to 0. So it's a 24 base system. Kind of unusual. I believe that actually came from the Romans, the 24 base system. Anyways, we're good. Keep on going. We have ourselves. Okay, that's all the angles we know of real quickly here. Here it is. There it is. Sometimes we put a little box like this for it. Sometimes we put this right here, but that little box means 90 degrees, right? And this is called a right angle. Let's see. And then the other one, straight across. Anybody know the name of this guy? That's the degree measurement, What's the name of this angle? Oh, line. Oh, yeah, that's so cool. Okay. Since it goes straight across, it's called the straight angle. All right, and these ones you probably should know, have known it for quite a while. There he goes. Yep, less than 90 degrees. We have an acute angle. And then we got this guy here. Greater than 90 degrees. You guys know obtuse angle, right? Okay. Jamming. Okay, and then we have the connection of two angles together here. So how about, oh, that's how you do it. Talk to me here. What do you guys say? Something like this, complementary angles. Anybody remember those guys?
It's like when the two lines cross each other, right?
Ooh, those are called vertical angles.
So they add up to, is it 180 or 360? Oh, no, it's when they add up to 360, it's like a full triangle.
Oh, perfect. Close, close.
180, right?
Oh, I know.
180 is smaller than 180.
It's the flat line where there's like one, and there's two angles on it.
That's awesome. Thanks, guys. Those are supplementary. We'll get into this a little bit. Complementary.
What's the, like, that's like the, is it the X, but there's like the angle on the opposite as well? There's like two lines and these angles are equal to these angles.
Oh, yeah, yeah. Those are called vertical angles. Vertical angles.
You got that.
Everything but the correct answer. But you guys are even close here. Less than 80, less than 180 degrees. With what is what's the degree that they had to add up? So how about this little guy right here? Complementary angles are two angles that add up to this guy here. What's the little box for? Right angle. So complementary angles are two angles that add up to 90 degrees or right angles. The way we write them out like this right here. We do the first one, first arrow goes out, that's alpha. We got another arrow that goes out, that's beta. And whenever we have two angles, normally it's written as alpha and beta, or sometimes A and B. That's kind of two. Okay. Complementary angles, what's so special about them is that alpha plus beta equals 90 degrees. Complementary. Okay. The one. Supplementary angles. That's what you guys were thinking about earlier. There it is. And this second angle could be wherever it likes to be, but you have an alpha plus a beta that makes a straight angle. So in this case, alpha plus beta equals 180 degrees. Okay, still jamming well? So now let's get to our first example here. Example number 1. So find the complementary and supplementary angles, or angle, actually, I should say. Let's see, part A. Let's do part A. All yours for part A. That's easy enough. You guys can do it in your head. Probably takes longer actually to. Cool. All done? Probably all done here. Yay, too easy, right? Mr. G, come on, can you make it even a little bit more difficult? Right? Uh, 130, is it? Is that true? Cool. All right, and of course, got to do the fun one here, 120 degrees. Cool, cool. All right. Did it take longer to write down the problem than it is to finish off the problem? Complementary answer is, oh yeah, now that we have negative angles, which we did not have before until today, we have negative angles, so we can actually use negative angles as complementary angles.
Wouldn't it just actually be a positive angle that takes it over 360 and sweeps back?
No, it is still, because the definition is what angle measurement adds up to give you 100 or 90 degrees. It's still negative. Is it negative 60? Sorry, negative 30? Negative 30. That is so cool. We're getting negative angles now. Will go away. Okay. Doesn't want to go away. That does not go away either. 1 second, class. There it is. Easy stuff. Okay, how about one last one here, just to completion's sake. How about theta? My angle is theta. So get more abstract here. So this one actually is just a formula, right? It's just gonna be like that. That's 90, subtract that value. Supplementary. It's going to be the formula for it, which is just this right here. Everybody good with that? Your exercise. That's good for you. All right, one more thing is this guy here before we do. All right, the theorem, you guys talk to me. What is it? I think we know it. Based upon what kind of triangle? Right triangle. Has to be a right triangle. And then the legs are A and B. The hypotenuse is C. And then let's label the rest of this here. So hold on, if my little legs are ABC, where are my angle measurements and how do I label them? And so what we do with triangles, talk to me if you learn this from geometry. Whatever is the angle opposite the side, that's the angle measurement with a capital letter. So that A is going to be across or opposite of little a. That B is going to be across from big B as the angle. And that C usually is the right triangle or the right angle, which is there. So good there. And some books even label saying C equals 90 degrees, just to make sure. But the little box would suffice for us. Okay, the Pythagorean theorem says that if I square the A, if I square the B, it will give me the square of C. And it's pretty cool that lots of people have trivia question for you guys on Wednesday, if you can look it up. How many unique proofs are there for the Pythagorean theorem? That's my question. If it kind of sticks to you on Tuesday, like, oh, Mr. Ng wanted me to find out. So how many unique proofs are there to the Pythagorean theorem? Second, another trivia question. Which US president actually holds an original proof to the Pythagorean theorem?
Is it currently alive?
No, not currently alive. So he actually came up with his own proof for the Pythagorean theorem. Say again? No, All right. So with that, let's see, let's do the exercise first, then we'll get into the other piece here. Jamming with number exercise 2. Let's jam with that one here. Homework. How does the homework write it? Solve. There it goes. Solve. Solve for x. Part A. All yours for this one. X is here, 5 is there, 13 there, and go. Should be a pretty easy one. And then, of course, make it a little more difficult one. Let's see, plug into. I like to put parentheses in, just so I know exactly what I placed in there here. That should give me x squared. That should give me what, 25. Anybody 13 squared? $169, perfect. Subtract 25 from both sides. X squared is equal to 144. Hey, that's cool. Okay. Do you guys remember whenever you square both sides of a square root? Normally we'll put plus and minus in there, right? Don't we? We put a plus and minus in there. How come I'm not going to do it right now? It's a length. It's actually a real object. And so this case, whoa. In this case, x is equal to 12. That's cool. Okay, one more, a little more difficult. You guys are already done, huh? You guys are terrific. Tristan, were you able to put it back?
Yeah.
Okay, cool. Okay, part B. Oh, that's what happened. Okay. Part B, how about this one? Again, all gearing up towards trigonometry. I haven't even started trigonometry. No fun. That is a 3. I'll write it over. Yes, if you can't read my handwriting, please ask me. I will correct it here. And whoever goes to the bathroom has to do the next problem.
I am solving for accident.
Yep, solve for X. I'm just kidding, Abe. I'm just kidding. This should be a little bit more of a toughy one here now. Let's see. So that means, and are you guys okay seeing the blue on here? Get this blue and darker. Let's see. I just forgot to put, I forgot to declare that this actually is a right triangle, so I guess I should do that. Then I got myself the work here, so. All right, from algebra, you guys remember how to multiply this out very, very quickly? How do you guys multiply x plus 12 to the second power? The slow way is to do it like this, right? It's x plus 10, another x plus 10, and you FOIL it out, right? That's going to be x squared. That's going to be a 10x. That's another 10x. And that's 100. And eventually we get x squared plus 20x plus 100. Okay, that's cool. Anybody know the fast way? Talk to me. Let's go for it here. Okay, let's see. The fast way to do it is, all we do, let me. That little guy does not look like a 2. 1 second here. Okay. All we do is we square this in front. We square this in the back. And we multiply these guys together times 2. You guys remember that from somewhere a long time ago in the land not so far away. So it's going to be x times 10, which is 10x, times 2 makes 20x. Ooh, okay. Good, bad. Raise your hand if you did it the short way. 1, 2. Raise your hand if you did it the long way. Raise your hand if you didn't raise your hand at all. Okay, cool. So x squared plus 20x plus 100. 100 doesn't look so nice. Okay, plus what, 9 is it, right? And 15 times 15, anyone? 225, thank you. Okay, so I got myself x squared plus 20x, so it's 109, 225. Okay, you tell me what to do next. Ooh, close maybe.
Would you subtract 225?
I think so, yeah, because we see the x squared there, we see the x, we know we're going to factor. And prior to factoring, what we have to do is we have to.
Wait, could you subtract 109? You can do that first, it would just be longer, right?
It'd be longer, and then what you would have to do is you have to do completing the square process on both sides, and then solve for x. So yeah, a lot longer, but still, yes, still doable. In fact, you would have to do that if they didn't come out nice. Ooh, you know what?
Oh, wait, it does.
Does it come out nice or no? See, I have a little problem this year too.
Oh, wow.
All right, you guys talk to me. Does it come out nice or no? What is 109 minus 225? 116?
Negative 160.
Negative 116. Okay. So now, okay, got a jam here. Let's see. Negative 116. I would see factoring now. I need two numbers to give me a negative 116, add up to a positive 20. So what, 1 and negative 116 would do it? I know 2 goes into it. 2.
2 and 60, 2 and 58.
58, uh-huh.
So smart.
Let's see, 6, 7, 8, 3 would not go into it. Do you guys know how to do division by 3? You add up all the digits together.
Doesn't that only work with 3-digit numbers, or does it work with?
They need digit numbers, yeah. So
I
3,
think double digits would be easier for us to remember.
let's see, 6 plus 1 is 8, so 3 would not go into it. Does 4 go into it? Yes, 4 has to go into it because 4 goes into the last two numbers is what 4 does. So 4, oh, I forgot to put the minus sign here.
4 and negative 29.
That sounds about right. So that's 25. Let's see, 6. Would 6 go into it? 7, maybe use a calculator here. 8. 9. No, none of it goes into it. Ah. What should we do? What should we do?
I feel like you have an answer. I don't. Why is the first problem so?
No, shucks. Oh, I know. Hold on, if we get stuck with factoring, what's the other process we can use? What's our default process?
Oh, quadratic formula.
Quadratic formula, all right.
Oh, why didn't we?
So let's see, negative b, right? So negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Ooh, let's see if this gets us anywhere here. Okay, anybody with a calculator here that can do that real quickly here? So it'll be 400 plus.
Well, you can already take out, just do -10 plus or minus. And do the whole division thing.
I'll have to take out the 10 out of here as well. So I'm not sure if 10 will come out of that.
Or no. Let's just get rid of 800. I probably did something wrong on that.
No, no problem.
Yeah.
Let's see, 24. That's 6. That's 4 plus another, yeah, 864 times 2.
Oh, but then it's divided by 2.
So this one's a calculator problem, looks like. Hold on. So if we have a negative in front, if we subtract more of the square root of a negative, is that even possible? I don't think so, because we're gonna have a negative answer for a real side. So only one to do would be, anybody real quick here? -20 plus the square root of 864. And after you do that, divide all that by 2, and what approximately do we get?
I can't. I got around 4, but that's
Around 4? Let's see, let's go back to our problem. What's our problem saying? That if this is 3, x would be about 4, so the side would be about 14. This side would be about 15. Does that look about right? I think so.
Wait, so I was
Yeah.
right? I got 4.696938.
Uh-huh. So about 4.6. This thing's not right for me. About 4.6. Okay, real quick here before we go, got one more thing to show you here. Let me pass this out. For everybody. The 2 special triangles. Let's go for it. This is your take-home assignment as well. To sort of see if you can do this here. I have a square.
So I'm not doing the first homework assignment tomorrow.
I'll see let's see where we're at on the homework right now. Okay, got this one. Let's pass this one out too. Da-da-da. So not the fact that you need 2 of them, but just in case you need to play with it and not get it to play with it again. Here's what I got. I need you to figure out this right here. I have a square. I have a square. And you're going to draw this in as well, real quickly here. Here's all I know. I know I have a diagonal that's coming across. And the diagonal measures exactly 1. Good there? I need to know, this is a square, so it's a right triangle. I need to know the length of this side, and I need to know the length of this side. This will be our homework for today. We'll not do 1.1 homework, we'll just do this one. Okay, so that's one part. That's your rectangle or square problem. The other one, you have an equilateral triangle. Equilateral triangle. All the sides are the same, all the angles are the same. Question is this: if I were to drop a hypotenuse down like this, oh, sorry, before I do that, all the sides are 1 already, 1, 1, and 1. And if I were to drop a hypotenuse down like this, I need to know the length of the hypotenuse, and then I also need to know the length of the small side there. Okay, we good there for a homework assignment? So think about, and then let's see, the trivia questions are, how many solutions are there to the Pythagorean theorem, and which president of the United States holds a original proof to it? No, that's just for us to get together on Wednesday and talk about. Cool. And we'll continue with that. And with that, have a good day.